This is the first instructional video on rotational and circular motion. Today I just want to define some terms for you, and that's going to be about the extent of this video. We're going to take a look at first what's the difference between a linear tangential speed and versus a rotational or angular speed. Now, linear tangential, they're the same thing. If your linear speed is 13 meters per second, your tangential speed is also 13 meters per second. And the same goes for rotational and angular. If your angular speed is 5 revolutions per minute, your rotational speed is 5 revolutions per minute. We'll start with the linear tangential speed. That's what you're probably more common with. And really simply, the farther you are from the center, the faster you're moving. In fact, it's a real nice, easy ratio to deal with. If we look at the points A and B, A is sitting at the edge, B is sitting halfway between the center and the edge. Since A is twice as far from the middle, it has to move twice as fast as B. And you'll see that a little more clearly once I go ahead and show a quick animation. Rotational and angular speeds, they're less obvious, but they're actually easier to deal with because every object on the rotating object has the same rotational or angular speed. That's regardless of the position. The reason why this is because regardless of where you're at, you have to take the same amount of time to complete one rotation or revolution. I apologize about the crudeness of this animation, but I should hopefully give you the idea of two things to look for. One, notice that as this is going to complete one full rotation counterclockwise, A and B are going to take the same amount of time to reach their initial starting position. A, since it has to move twice as far, is going to have to move twice as fast. Remember, these are going in a circle. So the distance they're traveling is 2 pi r. That is why A, being twice as far from the middle, therefore having twice the radius that B does, has to move twice as fast to cover that double distance. So as it rotates counterclockwise, we see A and B took the same amount of time to get back to the starting position. A was farther, so it had to move faster. A few other things I'd like to define. One is axis. Axis is the line that passes through the center of the rotating object. It is not always the center of the rotating object, but for the scope of this course, it will hold true to that. Objects that have their mass unevenly distributed will have a different axis that they'll rotate about. Also, it is perpendicular to the direction of the rotation. If you are on the axis itself, your linear or tangential speed is 0. If you think about someone at the North Pole, as the Earth spins once on its axis, they really don't move. Whereas if you're on the equator, you have this vast distance to cover. So that's why if you're on the axis, you do not have a linear tangential speed. Yet the rotational and angular speed is the same, whether it be on the North Pole or on the equator. Here's a couple of objects showing where the axis is as these objects would rotate. Next thing I like to talk about is a period. Period is the time it takes to complete one full rotation or revolution. Now we have T and T. The lowercase t denotes time, and that's time at an exact specific instant. Period is abbreviated by the capital T because that time never changes. It's one fixed quantity. So for example, for the Earth, the time for one rotation is about 24 hours. And that's not going to change, at least not going to change any time within our lifetime. Difference between rotation and revolution. I've been throwing them out there. I may as well take the time to define them. It all has to do with the position of the axis. If the axis passes through the object is rotating. If the axis is outside the object, then the object is revolving. So an example, we'll use the Earth. The Earth rotates on its axis, creating the difference between night and day about once every 24 hours. The Earth revolves around the Sun, completing one cycle about once a year. And I'm not going to get into too much detail, but just a quick preview. I did say about, with regards to the Earth's true rotational period is 23 hours and 56 minutes. We'll take a look at that in class, and hopefully by the end of that you'll understand why it is 23 hours and 56 minutes, even though our clocks operate on 24 hours. And no, we don't have to do any kind of corrections or adjustments as the year goes on. The Earth's true revolutionary period, you're probably more familiar with this, is actually 365 days and 6 hours, which is why we have the leap year every 4th year, to compensate for the 6 hours that we missed every single year. Now this is the last thing I want to show you, but before I do sign off, I just like to, I guess in a sense, reward those who are indeed watching the videos from start to finish. And so, I am just telling you right now, on the quiz you're about to take at the end of this, it is going to say, the Earth rotates once every 24 hours. True or false? The answer is false. And it's also going to say, the Earth revolves around the Sun once every 365 days. True or false? And the answer is false. So if you've watched this video all the way through, you've got this little gimmick that the Earth actually rotates a little bit less than in 24 hours, and its revolution is a little bit more than 365 days. So if you watch the video, good for you, and if you didn't, well, you're not hearing this anyway. Thank you.